Hello students, my name is Shayan Mitra. I am the faculty member of Department of Electronics and Communication Engineering of Greater Kolkata College of Engineering and Management. Today I am going to take the class of electromagnetic wave theory. The subject code is EC501. This is the lecture number 12. This is the continuation of the previous two lectures where we have discussed about the non-conducting uniform plane wave for non-conducting medium, conducting medium, which is also known as the lossless medium, and lossy medium as respectively. In this lecture, we are going to take this discussion at the further level where we are going to discuss about the uniform, another all the cases of uniform plane. We will complete this part and we will get into the wave polarization part. Okay, so let's begin with the lecture. Okay, so as we are discussing in the previous lectures, we have discussed about how we could take a analogy for a light wave and for any kind of electromagnetic wave where we when you have a electromagnetic wave which is propagating through a free space is basically got the speed of 3 into e to the power 8 meter per second for uh, their speed which is very much equal to the speed of the light. Okay, so the continuation of that we get into this kind of conclusion, and with this we can go to the next part of the PPT where the solution of wave equation, where we have already given the important consideration. We have taken the important consideration where we have taken into consideration that uniform plane wave which is traveling in z direction free space. So in that case, with the wave equation for electric field along the x-axis, y-axis, it could be rewrite here, and this it could be rewrite here as this. Okay, where you know the value of the wave at free space is 3 into 8 meters per second. Now the general solution of such differential equation has the form of from the first order derivative, this is the second order derivative of the general solution for this second order derivative is the differential equation where E is equal to f1 z minus ct and plus f2 into z plus ct. Okay, let's go to the next slide. The uniform plane wave traveling in z direction free space. Here f1 and f2 are any arbitrary functions of z minus ct and z plus ct. The function of z minus ct and z plus ct may assume any form as could be trigonometrical form or exponential form. It could be rewrite as a sine beta z minus ct, or it could be rewrite as a to the power beta z minus ct. The first function represents a wave traveling in positive z direction, while the second term represents a wave traveling in negative z direction. Okay, this is the first part and this is the second part. Okay, so let's go to the next slide. The solution of wave equation where the uniform plane wave traveling z direction in lossless or non-conducting medium sinusoidal time variation, we know the values that del square ex by del z square is equal to minus omega square mu f psi ex. Now putting those values, when you put the value del square plus del z square is equal to d square, we can or it's basically a second order derivative, we can rewrite it as a d square ey plus omega square mu f psi ey is equal to 0. From this equation we can derive this equation. Okay, from that we can get this equation which can be rewrite as a characteristic equation which is m square or m or d, you can take anything that we have put the value m in place of d, that m square plus omega square mu f psi is equal to 0. This is the characteristic equation of that specific wave which is traveling in the z direction. So the uniform plane wave traveling z direction lossless or non-conducting medium sinusoidal time variation, and in case of sinusoidal time variation you can rewrite it as a 0 and you get the value m plus minus j beta, where beta is omega root over mu f psi and also known as a phase constant. So hence the solution can be rewrite it as a electric field along the y-axis can be rewrite it as a e suffix m1 e to the minus j beta z plus e suffix m2 e to the power j beta z, and em1 and em2 are arbitrary constants. Okay, so the continuation of the previous slide is that the uniform plane wave traveling z direction in lossless or non-conducting medium sinusoidal time variation, where we rewrite this equation as from this part. Okay, this is the part which is deriving the forward wave which is propagating in the plus z direction, and this is the part which is propagating in the negative z direction. Okay, so it could be rewrite it from the it has been rewritten from the differential equation. When you put this del square by del z square as a d, this is providing us the characteristic equation. From that we can get the value m which is plus minus j beta, where beta is omega root over mu f psi and beta is also the phase constant of the wave. So the solution of that equation will be this, the second order derivative, the reference equation solution is this two part. The first part is deriving the propagation of wave in plus z direction, and z the plus z is deriving the propagation of z the wave in the negative z direction. So as we rewrite this value, so the above equation is the phasor form of the electric field. To find the time domain form, we multiply the phasor form by e to the power j omega t and then take the real part of it. So it, as we multiply this with this part and we take the real part, we get the value here as em1 by rearranging the parts. We can rewrite it as a em1 cos omega t plus beta z plus em2 cos omega t plus beta z. Okay, so these values, this is for forward traveling wave and this is for backward traveling, that we have already described. So from that we know that beta is equal to omega root over mu f psi and omega by beta is equal to 1 by root over mu f psi, so it could be rewrite as c. So propagation of light can be rewrite as omega by beta. Okay, so as we extracted the forward wave traveling wave equation and the backward traveling wave equation for a wave which is propagating in the z direction, and here we have the EY value, which is electric field along the y axis. Okay, so as we have these values, so you can rewrite it. I can also rewrite this cosine function in the form of sine functions, easily understandable. For now, for the phase of the forward traveling wave to remain constant, we have to have this value to be constant. Okay, so as t increases, z must also increase. This means that the wave travels in z direction with a constant phase. Okay, similarly for the backward traveling component, the same thing will happen. As t increases, z must decreases in order to keep the phase constant. Okay, this means that wave travels in the minus z direction with a constant phase. Okay, so phase will be constant for beta. To have the constant phase or the phasor value, we have to have this omega t minus beta z, this equation, to be a constant value. For with the increase of t, we have to increase the value of z, and the same way as we increase the value of t, the value of z must decreases for minus z direction. Okay, so from that we can understand another thing, there is a phase velocity. Now due to the variation of E with both time and space, we may plot E as a function of t by keeping z constant or vice versa. That thing we have already discussed earlier. So the wave takes distance lambda to repeat itself, and hence lambda is the wavelength, and also the wave takes time to t to repeat itself, and hence t is called the period of the wave. Since it takes time t for the wave to travel a distance lambda at the speed nu, the lambda is equal to nu by t, and so omega will be nu into omega is velocity. So as we know, t is equal to 1 by f, so it could be rewrite as the speed of the wave is multiplication of wavelength and frequency. Okay, so omega is equal to 2 pi f, so from that we can rewrite it as a beta is equal to omega by nu, or beta is equal to 2 pi by lambda. Okay, so as we know, omega is equal to 2 pi by f and f by lambda, so beta can be rewrite as a 2 pi by lambda. This is the value of the phase velocity, which is beta, which is equal to 2 pi by lambda. Okay, so this with this specific mathematical calculation, we got into the part, and depending on the differential equation and from the exponential function, we rewrite this equation and we get the phase constant. Okay, so let's go to the next slide. Okay, so as we have discussed about all those part, we have discussed about the incidence of uniform plane wave, how we can conduct a uniform plane wave equation using a lossy conductor or conducting medium, or non-conducting or lossless medium. We also consider how we can establish the relation of phase constant and attenuation constant, also the relation of phase velocity. We have gotten to the part where we have understand that any kind of wave which goes through the free space can have the speed of light, and we have discussed it and proved it with the mathematical postulates. And we have discussed about the different kind of uniform plane wave equation depending upon the parameter which have been considered. So after covering all those part and also describing that uniform plane wave equation in a differential form, we put those value, we extract the forward wave equation and negative wave equation, wave that is propagated in a plus z direction, and a wave which is propagated in the minus z direction. Okay, so after doing all those part, let's get into the next part, where we are going to get into the more definitive part, where we have a diagram of the tree for electromagnetic wave, which is constructed of plane waves. Plane waves are related to the lossless medium, lossy conducting medium, good conductor, and good dielectric. So we'll go through this part we'll go through the polarization part, and we'll go through the Poynting vector and plane waves in various media. So plane waves in various media, this two part has been covered, this two part is going to be covered, and this part and polarization. So in this lecture and the upcoming next lecture, we are going to discuss about the polarization and the uniform plane wave equation in different medium. Okay, so let's begin with it. So the plane waves, that the definition that you have already got, that what are plane waves, that waves are a means for transferring energy of information from one place to another. What are EM waves? Electromagnetic waves, as the name suggests, are a means for transferring electromagnetic energy. Why it is named as plane waves? Mathematically assume the following form, that function of r and t is a function of r, which is the position vector, and t is a time. Okay, and it could be rewrite as e to the power jk. That specific equation has been established earlier, so we don't get into this part. So next, now where k is the wave vector and points the direction of the wave propagation, r is the general position vector that we have already discussed, omega is the angular frequency, and f0 is a constant vector. Now f0 denotes either an electric or magnetic field, or for example in electromagnetic waves, f0 is either vector electric field or magnetic field, that we have already discussed. So the in rectangular Cartesian coordinate system, it could be rewritten as this, k as a the value of kx components goes to the x axis, y axis, and z axis depending on the equation. R will be rewrite as this, and this can be again rewrite as the constant phase surface for such waves as this. Okay, now plane defines a plane surface, and hence the name plane waves. Since the field strength is uniform everywhere, it is also known as uniform plane waves. A plane wave is a constant frequency wave whose wavefronts are infinite parallel planes of constant amplitude normal to the phase velocity of vector. For plane waves, from the Maxwell's equation, the following relation could be derived as this, that we have already discussed. The properties of a uniform plane wave: the electric and magnetic field are perpendicular to each other. No electric or magnetic field in the direction of propagation. That's why it is known as transverse electromagnetic wave, which is TEM wave. The value of the magnetic field is equal to the magnitude of the electric field divided by eta 0, which is the characteristic impedance, okay, at every instant, which is as 377 ohm. The magnetic field amplitude is much smaller than the electric field amplitude. Okay. The next one is the direction of the propagation is in the same direction as Poynting vector. The instantaneous value of the Poynting vector is given by e square by eta 0 or a square by eta 0. The average value of the Poynting vector is given by e square by 2 eta 0 or a square by eta 0 by 2. The stored electric energy is equal to the stored magnetic energy at any instant. That's a very important part. The stored electric energy is equal to the stored magnetic energy, okay, at any instant. The wave polarization, and the wave polarization part is the polarization of a plane. Now as we have discussed all the two various medias, we will get into the two medias in the next chapter, but in here we are going to go through the polarization part. Okay, now wave polarization. Polarization of plane wave refers to the orientation of electric field vector, which may be in fixed direction or may change with time. Polarization is the curve traced out by the tip of the arrow, representing the instantaneous electric field. The electric field must be observed along the direction of propagation. Now we'll go through the part where the types of polarization have been here. The polarization are linear polarization, circularly polarized, final, and elliptically polarized. The circularly polarized are divided in two parts: left hand circular polarization, right handed circular polarized. In case of elliptically polarized, both are also been applicable for right hand elliptically polarized and left hand elliptically polarized. Now in case of plane waves, if the vector that describes the electric field at a point in space varies as function of time and is always directed along a line which is normal to the direction of propagation, the field is said to be linearly polarized. If the figure that electric field trace is a circle or ellipse, then the field is said to be circularly or elliptically polarized. Besides, the figure the electric field traces is circle and anti-clockwise or clockwise direction. Then electric field is also said to be right hand or left hand circularly polarized. Besides, the figure that electric field traces is ellipse and anti-clockwise or clockwise direction. Then electric field is also said to be right hand or elliptically polarized. Now let us consider the superposition of a x linearly polarized wave with a complex amplitude Ex and y linearly polarized wave with complex amplitude Ey, both traveling in positive z direction. Note that e suffix x and e suffix y may be varying with time for general case, so we may choose it for a particular instant of time. Note that since the electric field is varying with both space and time, so it will be easier to analyze a particular instant of time first, and at the time dependence later, the total electric field can be written as that you have already this that e suffix ex plus e suffix y e to the power minus j beta z could be rewrite as this. Note e suffix ex, e suffix y may be complex numbers, and e suffix x0 and e suffix y0 are the amplitude of ex and ey. Okay, so first let us understand. Now let us understand that what we have discussed up to this point. Okay, up to this point is that when you are talking about polarization, so first we have to understand that up to this point what we have discussed, that a specific wave, when you are talking about a specific wave, that how a specific wave can be generated. A specific wave can be generated by using an electric field or a magnetic field. Now how do you generate a using electric field or magnetic field, how you generate a specifically oriented, specifically with a specific direction, we can have a electromagnetic wave, a transverse electromagnetic wave. A transverse electromagnetic wave can be generated by launching a electric field along the Ex component. Now what is that Ex component means? Suppose there is a point electric field, which has two components, e suffix x which is along the x axis, e suffix y which is along the y axis. Now if we generate electric field along the axis of E, we have two components. Now we take the reverse engineering process and we generate an electric field along the components of the electric field. Now suppose we want to have an electric field along the x axis. Now to have that electric field along the x axis, that specific electric field after generated, it will have two components, which is also known as e cos theta and e sin theta. So to generate the real resultant electric field, we will generate an electric field along the Ex component and the Ey component of that specific electric field. Now as soon as we generate the Ex and Ey, both by their vector addition method, it will create an electric field which is along the x axis. Now as soon as we created an electric field along the x axis, another magnetic field will be automatically be generated at the y axis. Now as we have an electric field along the x axis and a magnetic field along the y axis, it means both are orthogonally related. Now depending upon these two electric field and magnetic field, we will have a propagating wave which is propagated in a z direction. Okay, so one along the E, along the H, and it will propagate along the Z. Okay, so as soon as we create an electric field, depending upon that there will be another magnetic field will be created orthogonally, and depending upon that, depending upon the electric field and magnetic field, there will be another wave which will be directed towards the Z direction. It means a wave which is orthogonally related to the electric field and magnetic field, and also been related, also the electric field and magnetic field are orthogonally related to each other. So three wave which are transversely related, okay, wave will be created only just by creating one electric field with proper sequence or proper direction. If we can generate an electric field with proper direction, if we can generate a electric field with a proper direction, we can be able to create a transverse electromagnetic wave along the z direction, depending upon in which way we want to have that wave to propagate. So depending upon that, we will create the electric field, and as soon as we create the electric field, the magnetic field which will be related to that electric field will be created. So three wave which are orthogonally related to each other will be created. That's why it's also known as transverse electric mode. And now as soon as we use those process to create electromagnetic wave, where now if we take a top view look of now if we have to take a top view look of the electric field, so as the wave propagated, with that the electric field and magnetic field will also be propagated. So the linear polarization or circular polarization, elliptical polarization is nothing but the tip point of the electric field. Is the electric field, the direction of the electric field, the tip point of the electric field, which can be uh, viewed from a from a side perspective. So that is the polarization of a specific electromagnetic wave. Okay, so depending upon that we will going to discuss about the polarization. Okay, so let's go to the next slide. Now as we know that plane wave easier to analyze at particular instant of time. First, an added time dependence later. The total electric field can be written here as that. Note Ex and Ey may be complex numbers, and Ex0 and Exy are the amplitude of Ex and Y. Now phi x and phi y are the phases of Ex and Ey. Putting in the time dependence and taking the real part, we have E suffix zt can be rewrite as a e suffix x0 cos omega x minus bz plus phi z x, Ey0 cos phi minus beta z plus phi y. A number of possibilities arises. Linearly polarized wave have, if both the Ex and Ey are real, say Ex is equal to E0x or Ey is equal to E0y, then E at left polarized z will be rewrite as E suffix x plus E suffix y cap e to the power minus j beta z, and the same will be dependable for that. E suffix 0x and E suffix 0y can be replace the E suffix x and E suffix y. Okay, so up to this, we have understand what is the polarization means. Now in the next lecture we are going to give a detailed analysis of linear polarization, elliptical polarization, circular polarization, why it is awake, why depending upon the direction or the angles of the formation. Okay, depending upon, as we know, the tip of the electric field, as the tip of the electric field will take its analyzing position, depending upon that the tip will take a we make a drawing of the electric field. So depending upon that we will create the polarized picture or the polarization value of the electric field. Okay, so that's so the linear polarization, elliptical polarization of electromagnetic wave will be discussed in the later lecture. Okay, so with this we are going to conclude our lecture here. We are going to take a deep dive about the linear polarization, elliptical polarization in the next lecture. Okay, so thank you. We are going to end this lecture here now. Okay.